So we've talked about all different types of things that go into calculating forces, acceleration, all that kind of stuff. Now we're going to take our forces and we're going to put them on an incline. Okay? And to do that, we need to review just a couple things before we can dive in to looking at some free body diagrams with an incline. Okay, so I just want to talk through a couple of these forces to begin with. Okay? The normal force is the force that the surface exerts on the object. Okay, would we agree with that? Yes. So what direction does it normally go? Right, straight up in the air. So far, we've looked at diagrams, free body diagrams that look something like this. Right, where our normal force goes straight up in the air because it's sitting on some surface, right, some horizontal surface. Now the difference will be our object is sitting on an incline. Right? So will the normal force go straight up like it has in the past? No. It's going, perpendicular to the surface. Okay? So now the normal force always goes perpendicular to the surface. Okay? It's not necessarily straight into the air. It's perpendicular to the surface. Okay? The gravitational force, however, stays the same. So again, if I have a gravitational force on a regular object, right, it goes toward the center of the earth or straight down. Okay? But when I start looking at it on an incline, does gravity act at an angle like that? No. So gravity still is going to pull straight down, and the normal force goes perpendicular. So these two forces no longer 100% offset each other. Right? So we're going to have to shift our thinking a little bit in terms of the forces that are acting here and how we can look at offsetting them. Right? So our gravitational force still pulls it straight down all the time. Okay? Sorry, you can put that in your notes if you'd like. But normal force perpendicular to the surface, gravitational force pulls straight down all the time, okay, regardless of the situation. Okay, so when we're working with inclines, we want to try to avoid using forces at an angle, right? Because anytime we have forces at an angle, we have to break it down into its x and its y components, and it's a lot of work. So if this were sitting on a regular coordinate system, right, if we had a regular coordinate system, and our box was on an incline, we would have a normal force that's at an angle, we could have friction that's at an angle, we could have applied force that's at an angle. The only one that would still be on the axes was the gravitational force. Does that make sense? So that's a problem, right? That's 3 forces that are at an angle. That's too much work for us. So what we're going to do is we're going to tilt our axes in our coordinate system so that it sits along the incline. Okay, so now this becomes the positive axes, this becomes the positive, negative, and negative. Does that kind of make sense? So all we're doing is shifting the way we look at the coordinate system so that when we have the normal force, an applied force of some kind, a frictional force, see, those are all now purely horizontal or purely vertical. The only force that we see that's at an angle at this point is gravity. Does that make sense? So we go from 3 forces at an angle now to only 1. Okay, so by tilting our axes, we are eliminating the need to break every single one down into its x and its y components. Okay, does that make any sense? A little bit? Okay, so why do you think we chose this to be the positive direction? Yeah, it's still to the right, and most of the time when you put something on an incline, is it going to go down the incline or up the incline? Down the incline. So if we drew our incline this way, right, we'd still say that down the incline is the positive direction. Okay, so that's just something to think about. We always want to kind of just think about which is the most likely, right? So down is going to be more likely than not, so we'll choose down the incline to be the positive direction. Okay?
So if it was tilted the other way, you would have switched it?
Yeah, so if it was tilted, let's see here. If I had drawn my incline like this, I would choose this to be the positive direction and that to be the negative direction. Okay? All right, any questions so far? Okay, so we have to know how to draw our inclined. Okay. So now let's look at how we deal with the gravitational force, which is at the angle. Okay, so here's my object, right? I've got a normal force that goes there, and I've got gravity, which goes straight down. Okay, we're going to work with the components of the force due to gravity. Since our axes run like this, right, we now have a force that's at an angle. Okay, would you agree with that? Okay, since our axes look like that, our gravitational force is at an angle. So now we're going to break that gravitational force into its components, into its x and its y components. Okay, so those white dotted lines are its components. So now this would be its y component and its x component. And those specifically have names. Okay, the x and the y component of the gravitational force have names. Okay, since this force equals this force most of the time, right? This is our normal force. We also call this one normal force. Okay, because these two forces should be congruent. For all the problems that we are going to do, we're not going to dive too far into some more complex problems, but for all the problems we're going to do, right, these two should be equal to each other. Okay, so the vertical component of that gravitational force is equal to the normal force. This force that's on its x-axis is called force parallel. Okay, so this little is a parallel, not an 11. Okay, why do you think it might be called force parallel? Or the parallel force? That's right, it's parallel to the x-axis or parallel to the incline, exactly. Okay, so that x component of gravity is always going to be our parallel force. Okay, so when we say normal force and parallel force, we're talking about the x and the y components of gravity. Okay? Nope. Nope. So since these are congruent, we're still just going to say like we're identifying what that is. Good question. Okay. Something else that we can think about is when our incline is given to us, usually it's going to tell us what angle our surface is being inclined at, right? It might say it's sitting on a 20-degree incline. Okay, that 20 degrees fits right in here into our gravity triangle. Okay, these two triangles are similar, so you'll see this 20 degrees fits right into here. So whatever the angle is of our incline itself, it fits right into our gravity triangle there. Okay? So as we're drawing this gravity triangle, you have to make sure that FG is your hypotenuse.
Where does that one come from?
The 20 right here?
Yeah.
Okay, so if it says it's on a 20-degree incline, right? That's the level at which our surface has been, inclined up, but it also just corresponds with this angle right here, that gravity triangle. So I just made up 20, but in a problem it'll tell you the degree of the incline. Okay? FG always needs to be your hypotenuse. Always, always, always. So that means you need to make your right angle opposite of your hypotenuse. Okay, some people will try to draw it so it looks like this. Okay, so your right angle should not be there, right? It should be opposite of your hypotenuse. So just be really careful with that. Okay? Last little thing I want to talk about, how will we solve for FG? How do we find the hypotenuse of that triangle? What's FG always equal to? Mass times 9.8. That still applies. Okay, so when we're trying to solve for FG, if it gives us a 50 kilogram mass, we take 50 times 9.8, and that's our hypotenuse of that gravity triangle. Okay, so solving for FG is still the same math. Okay, a 10 kilogram box is sliding on a frictionless incline. The incline makes an angle of 30 degrees with the horizontal. So I'm gonna write out all the steps that we're gonna follow. You don't have to, necessarily write these steps down, but if it helps you to have them all written down, this is kind of the order we're going to go in, or a general order to go in to solve. The overall goal here is the acceleration of the box. Okay, but to get there, we got to go through several steps. Okay, so I'll give you a second to get written down what you need to, and then we'll draw what it looks like, and we'll start working the math. Okay, did everyone get a diagram that looks something like this? Okay, it's frictionless. Let's say if we needed to talk about friction, which direction would friction go, do you think? Up the incline or down the incline? Up the incline, right? Since it's sliding down, it would be opposing its motion. So we don't have any applied force here because we're not pushing it down the angle. It's just the weight of the box itself, the parallel force, is pulling it down the incline. So there's no applied force. We're not pushing it at all. There's no friction. Okay, so the first thing we're going to do is we're going to solve for the force due to gravity. Okay, and since it says our angle is our incline is at a 30-degree angle, that means that 30 degrees also goes right here. Okay, always to the angle that touches the object, okay, or touches the origin. Okay, so it says it's at a 30 degrees, so this 30 degrees is the same one that goes into your gravity triangle. Okay? First thing that we need to do is solve for FG. So how do we solve for FG? Mass times 9.8. So 10 times 9.8 equals 98 newtons. So now 98 newtons is the hypotenuse of our triangle. Okay? So when it says solve for normal force, we're solving for the which side? Adjacent or opposite side?
The normal?
Yeah, normal right here.
Adjacent.
It's adjacent to this 30 degrees. Right, here's our 30-degree angle. The normal force is adjacent. So which would I use, sine or cosine? I would use cosine. Oops, sorry. So I'll take 98, your hypotenuse, times cosine of 30. We want to make sure our calculator is in degrees, not radians. For these problems in your gravity triangle, you can memorize that normal force is always cosine, parallel is always sine. Always, always, always. Okay, that's one of the rare ones that we can use as kind of a rule. Okay, so normal will always be cosine, parallel will always be sine. Okay, so 98 cosine 30 gives us 84.9. And for the parallel force, we will use sine, so 98 sine of 30. And I get 49 newtons. Okay? So now we've found the force due to gravity, we've found the normal force, we've found the parallel force. We want to find the acceleration of the box as it slides down the incline. So do you think we're looking for vertical acceleration or horizontal acceleration? Okay, so that means we're only really concerned with our horizontal forces, which means we really truly didn't need to solve for the normal force, but oh well. Okay, so how many horizontal forces do we have?
2.
Okay, where's your other ones?
I would say 3 because frictionless. Force applied.
Yeah, no friction, so it's frictionless, so none of that. We don't have a force applied, so just parallel is the only horizontal force we have acting here. So the only thing that's pulling it down is gravity itself, right? Gravity is the only thing that's pulling it down. So when we set up our net force equation, we would say F parallel, and then you can do minus 0 if you want, or you can just leave that minus 0 off, right? Because there's nothing that's opposing that motion. Okay, so then our parallel force we know is 49. We're solving for acceleration, so what can we substitute here for F net? Mass times acceleration, so 10 times A equals 49. And that gives us an acceleration of 4.9 meters per second squared. Okay, an object sitting on an incline. It tells us the length of the incline or the distance the object travels, and it wants to know time. So we're looking at a little bit more complex than the last one.
So it doesn't matter which way it goes.
Doesn't matter if we draw our incline, this way or this way. It makes no difference. I just, for some reason, always draw them here. Okay, but that's totally up to you. If you want to do the other way, that's fine.
Is that point always going to go down in the same spot? Is it ever going to go?
FG will always go straight down. Okay, our incline is frictionless. We don't have any other inclines. Something to think about is these are not forces, right? That's just me drawing the incline itself. Does that part make sense? If it's a force, it would be using a vector, which means you'd see an arrow at the end. Okay, so that part is just the incline itself. So I'll try to have that in a different color, but those are not forces. Okay, so the only two forces we have acting here are gravity and the normal force. And we need to break down that gravity triangle into its x and its y components. Okay, drawing that gravity triangle is really important. Make sure that your right angle is opposite your hypotenuse. Okay, so this side would be called what?
Normal.
Okay, adjacent or normal. Good, so normal force. And then the x side would be called parallel. Okay, it tells us that our incline is 33.3 degrees, so that goes right here. Okay, I didn't quite draw it big enough to write 33 in there, but 33.3 degrees goes right here in our gravity triangle. Okay, always the one touching the axes. Okay, now this one, we want to look at how long it's going to take, so eventually we're going to have to find our horizontal acceleration and use a kinematics equation to solve for time. Okay, does that make sense? Because nowhere in our net force equation does it allow us to solve for time. So we have to find acceleration first, and then we can move forward to solve for time. Do we need to worry about vertical forces here?
No.
So we don't have to solve for the normal force, just like we didn't have to solve for the normal force in the last case. Okay? Instances in which we need to solve for the normal force are when we have friction, because it's coefficient times the normal. Okay, so that's the only time. Yeah, Griffin?
Do we need to multiply 466 by gravity?
No, that's right. That's right. Okay, so this right here, 466 newtons, it's already given to us in newtons, which means it has to be a force, right? It's already a force. If it's kilograms, that means it's its mass. If it's newtons, that means it's already a force. So that's equal to Fg. So you don't have to multiply it by 9.8. Okay, they already did that for you. Okay, so since it's in newtons, they already took it times 9.8. So later, when we need to know the mass of the object, we're going to have to take this number divided by 9.8 to find the mass, right? But for right now, we don't have to do anything with it. Okay, so let's solve for the parallel force. Parallel is sine, so we'll use 466 sine of 33.3. Okay? Now when I set up my net force equation, I would say parallel minus 0, right, or I could leave that off. because there's nothing opposing our motion here. So my parallel force, which is 255.8, is equal to mass times acceleration, right? We have to solve for acceleration in order to get to solve for time, but we need to know the mass. Okay, so since we know Fg is equal to 466, we take mass times 9.8 equals 466, and we divide that by 9.8 to solve for our mass. Okay, does that part make sense?
Yeah.
This was given to us as Fg, so to solve for mass, we take 466 divided by 9.8. That should be something, hopefully, that we feel really comfortable with by this point. Okay, so my mass is 47.6. Solving for acceleration equals my parallel force.
And that's in kilograms?
Yep, that's right. Mass is kilograms. Okay, so I plugged it in over here for mass times A. And I get an acceleration of about 5.4. Okay. But is that where I stop? No. So now I need to look at my kinematics equations. So if you don't have those out, you might want to grab those. Okay, your kinematics equations will allow you now to solve for time, because we have a couple different variables that could help us do that. Okay, we know our distance final is 8.45 meters, right? We're assuming it's going to travel the whole length. We know our acceleration is 5.4. What does this mean when it says it starts from rest? What variable does that tell us? Good. VI is equal to 0. Good. So what kinematics equation do you think we could use to help us solve for time? Which one? The first one, we don't have final velocity. So probably the second, right? The second one, we don't need final velocity. We know our initial displacement is just 0, right? DI is always 0. Okay? So I'm going to get rid of some of this here so I have some room. So the second one would say 8.45 equals 0 plus 0 plus 1/2 a t squared. So don't forget to square root that answer at the end, because you have t squared here. Okay, we're going to try one with friction. I didn't put out all the steps because they're going to be very similar, but our goal is to solve for the acceleration of our box. Okay, so now we have to take into account friction. So in the past we've only had one horizontal force, now we're going to have two. Okay, Okay, in our problem when it says 50 degrees with the horizontal, that just means still regular 50 degrees. Okay, so that means 50 degrees sits right here. Okay, so I would call this side normal and this side parallel. Okay. So now, since we're solving with friction, we have to take into account the normal force. Okay, so now we have to have both of those things. Okay, so when you're looking at incline problems, it's never going to hurt you to solve for everything just to start. But that's totally up to you. If you want to really examine what you're going to need, that's fine. But it's not going to hurt you to always solve for those two. Okay, before we can do any of that, though, we need to solve for FG. So how do we solve FG? Yep, good. 20 times 9.8. Okay, 196. So that means that is the hypotenuse of our gravity triangle. Okay, so to solve for the normal force, I'm going to use cosine. And for the parallel force, I will use sine. Are we at least pretty comfortable with solving for those two components, normal and parallel? Okay. Okay, so you can go ahead and solve for the frictional force, if you'd like, before we even plug anything into our problem. Okay, does that make more sense to you, or you want to plug it in the net force right now? Okay. Yes, I can. Sorry. This is the coefficient. So I'm going to go ahead and solve for the frictional force before we put anything into our net force equation. That way we can just plug in numbers when it's time. Okay, so to solve for our frictional force, we take the coefficient, which they told us is 0.4, times our normal force, which we solved up here, was 126.
They can give us that formula.
Frictional force, this one right here? Yeah, I'll give that to you. Coefficient times the normal. Okay, so we got about 50.4 newtons for our frictional force. Okay, so now we have our parallel and our frictional, and so we can start setting up our net force equation. Right? We want to find the horizontal acceleration of the box. So we're going to look at F net in the horizontal direction. So how many forces do I have acting in the horizontal direction? 1 and 2, right? And which one's positive and which one's negative? Which is our positive force? Parallel, because it's going down the incline, and our negative force is friction, okay, because it's going up the incline. So my parallel force is 150. My frictional force is 50.4. And I want to solve for the acceleration, so I need to substitute right here mass times A. Okay, so we get an acceleration really close to what? 5. Okay, try this one on your own. You can do it. How fast will it be moving when it gets to the bottom? So you're looking for final velocity, right? So to get there, you got to do acceleration first, and then you can go kinematics. Okay? So, go for it.